I'm Ruy Pinto. I'm the Chief Technology Officer of SES, and I'm here to talk about a cool piece of technology. It's called SES-17, and it's our latest geostationary satellite. In order to talk about SES-17, I will start by talking a little bit about one specific customer and how SES-17 is serving that customer. So we designed this satellite to cover the Americas, the whole of the Americas. So you have sort of the Americas here, including Argentina, Brazil, Central America, and so on. We have a customer called ComNet. ComNet is a data network supplier that uses beams in SES-17 over Central America. 3 beams. And what do they do with those 3 beams? They provide services for agriculture, finance, energy, education. So they connect companies, they connect enterprises. And the interesting thing about ComNet is that it's a good example of what SES-17 can deliver and what is the technology behind SES-17. That's what makes this whole talk interesting. For me, it's just about how can we deliver that connectivity from space, to be precise, from 36,000 kilometers away from the surface of the Earth. Let's start talking a little bit about SES-17 here. The first thing that I want to talk about is what sort of satellite SES-17 is. SES-17 is a high throughput satellite, and high throughput satellites are satellites that do what it says on the tin. They provide high throughput to small beams on the surface of the Earth. SES-17 is one of the latest generation of high throughput satellites, and they have what we call DTP. DTP, another acronym, so we'll go on the acronyms here. And a DTP, for people that don't know, it's a digital transparent processor. What does that mean? That means that it processes the signals that it receives from the Earth and that it beams back to the Earth digitally, right? At the baseband level. It is transparent, it doesn't change them, and it processes them. The latest generation of the DTP that we are carrying on SES-17 has a bandwidth. It's the amount of bandwidth, the amount of frequencies that it can process. It can go up to 200 gigahertz. We normally use around 160, but it goes to 200 gigahertz. It's a big beast. It has 18 power supplies the last time I checked. And one of the aspects of SES-17 and its latest generation DTP is that it allows us to route the traffic where we want. See, I draw here 3 spot beams that ComNet uses. They come from 3 gateways, right? Access points on Earth. So 2 are in Canada, London, Ontario, Winnipeg, again in Canada, and Santiago, in Santiago do Chile. So I'll just put these 2 here. And what you have is that you have the satellite here. And as any good big HTS satellite, this is not exactly in proportion, but it receives the signals from these 3 spot beams and distributes it via these gateways, and vice versa, right? So it goes up and down, it goes up and down. And the heart of the satellite is the digital transparent processor that processes those satellites. And you can see, for those that are a little bit more of a tech mind, that 200 gigahertz is a lot of processed bandwidth. That allows us to process up to 400 gigabits per second in the satellite, connecting all the spot beams and gateways. I only did draw the ones for ComNet, right? London, Winnipeg, and Santiago. But you could have up to 16 gateways, and you have 168 user beams that you can imagine them covering all of the Americas here. We could have, let's say, another beam, user beam in Bogota, Colombia, a couple here, 3 here. And you can connect these beams to other gateways. We have currently 8 gateways, but we can have more gateways. That's the sort of flexibility that you have, and the DTP is at the heart of that flexibility. Now, I was mentioning that this is a big beast, and now I'm going to talk a little bit more about the ins and outs, the size, the function that you have on such a satellite as SES-17. Let's talk a little bit about what is inside the SES-17. As I mentioned, SES-17 is big. Now, big is not necessarily beautiful, but in this case, it packs a punch. And if we look at it here, I'm going to draw it again. Here you have one solar array, you have the middle of the satellite or the body of the satellite and the other solar array. Just to give you an idea. And one way of comparing for some people is that from tip to toe, SES-17 is the height of Niagara Falls, and that's 48 meters from top to bottom. Now, for people that don't relate to Niagara Falls, we can compare it to an Olympic-sized swimming pool, 50 meters. That's the tip to toe again. It doesn't fly like that, right? It's the size folded inside the rocket that launches it. It's the size roughly of a double-decker bus. So you look at it and I said, oh my God, this is big. It generates up to 25 kilowatts of power. That's another good statistic that I like. If you think about 25 kilowatts, that's a lot of power that is coming from those solar arrays. Now, we don't use all that power all the time. Normally, when it's operating under nominal conditions, it will be using around 16 kilowatts. But we have margin. In the satellite business, remember when we launch one of these things, in this case on an Ariane 5, it costs a ton of money to manufacture and to launch, and we cannot fix it once it's in orbit. It's there forever. So we like to have margins. So here we have a margin between 16 kilowatts and 25 kilowatts, so that as the solar arrays degrade over life, as you have, radiation and aging and so on, you have margin in terms of power. Without power, a satellite dies. So it's very important to talk a little bit about the power of the satellite and how it generates. And just to recap, the 168 user beams and the 16 gateway beams. And even though I didn't put it there, I'll repeat it again. You have full connectivity between user beams and gateways and between user beams and user beams. Just imagine the Americas and you have all these, I love that, all these beams, which essentially draw the Americas. If you could imagine this as being North America, South America, and Central America, you'd be doing a great job. And you have the 16 gateway beams. One here, two here, there are a couple here. In fact, if I go back here, we have beams that crosses the North Atlantic because we serve the aero market as well. So planes that go from Europe to America and from America to Europe can use the SES-17 and they will cross over all those beams. This thing here not only has to last 12 to 15 years, but it's in a harsh environment, right? It's in the vacuum. It's subject to solar sailing, solar radiation, solar weather. It doesn't have any connection to anything else. It has to survive by itself. And of course, it has to survive eclipses. What do I mean by eclipse? Let's put here the Earth, right? If we imagine here the Earth and the Americas here. So the satellite is illuminating the Americas. And here you have the sun illuminating the satellite, right? Now, there will be times over the year where the Earth will obscure the sun. Therefore, you don't have power on the solar arrays. That's not very good. So you carry batteries. We carry 2 huge batteries inside the satellite so that you can generate still the same amount of power just on the batteries, sometimes for over an hour or so during these eclipse seasons. If you have all that power in vacuum, one thing that people don't necessarily realize is that if you are in vacuum, you don't dissipate the heat naturally. If you're pointing to the sun, you are very hot. If you're pointing away from the sun, you're pointing into cold space. For example, you have your laptop. Your laptop has a fan, right? And it's throwing out hot air, and you are recirculating the air. You don't have that in space. You have to rely on the heat that you generate inside the spacecraft. You have to transmit it out. You have to connect to surfaces out to vacuum. But sometimes that is not enough. So on SES-17, we had to create what is called a mechanically pumped loop, which, you know, it's a fancy version of perhaps a fridge. It's a heat exchanger. If you look at the DTP, which processes this 200 gigahertz, and if you were not to have any way of conveying the heat generated by the electronics in the DTP to outer space, it would just melt. You have to keep it between 20 and 40 degrees Celsius, and you have to transmit the heat that it generates to the outside of the satellite. And we do that via the mechanically pumped loop. Essentially, it's a bunch of ammonia tubes that exchange the heat generated by the DTP and some other electronics and essentially conveys it to the outside. It sounds simple because, you know, you have air conditioners, fridges and all that sort of stuff, but remember, that's in space. It has to survive the harsh environment in space, and if you were theoretically inside the DTP, sitting down and looking around, you'd be at a comfortable 20 degrees, when outside it's minus 273 degrees Celsius on the cold side, and it's really hot if you're facing the sun. Designing that was one of the challenges for the engineering teams at SES and Thales. The other thing that is also interesting is that I'm talking about processing and, you know, getting beam number X to talk to beam number Y or to gateway number Z or any combination thereof. But you have to power that. So we have what we call flex TWTAs. TWTAs are essentially amplifiers, traveling wave tubes. We can combine these TWTAs, and if you have, say, you are over Colombia, you know, really use your imagination and think Colombia is here, right? And you have more users in Colombia than you have in, say, Central America. You can combine these TWTAs and provide a boost of power. You can almost double the power over Colombia for a period of time so that you can serve more customers and provide more capacity. And all that is in this simple drawing here. We are really proud that we're able to fly it, that it's providing services to our customers over the Americas, that is at the forefront of technology for high throughput satellites. The teams at SES that worked on it were delighted to just see it providing and making a difference, connecting schools and connecting cruise ships and connecting airplanes. There is every reason for all of us to be proud that SES-17 has delivered its promises.